Hi 13 doubles. I thought I'd do a quick video on the challenge question on page 60. I think this is really good fun, this question. This summarizes the chapter nicely. If you can do this question, you can do this chapter and you'll probably fare very well in the next chapter as well. It's a toughie, there's no doubt about it. But what's more, it's showing you the maths that guarantees that when those light rays or radio waves or whatever they are, I'm no physicist, I've always said that, but when they hit your satellite dish, they all go through the same little point, which is normally where the aerial protrudes, so you can actually pick up all the signal. Essentially, this is how all parabolic lenses work. This is the focus, and this is the reason why we call, why the focus is important to parabolas. Basically, light rays coming in that direction. And it doesn't matter which, whereabouts they hit on the dish, they're always going to reflect onto the focus, yeah? And the way that works is because of the normal to the parabola and the fact that the normal to the parabola will bisect the angle between the line which lies parallel to the x-axis and the line which joins the focus to the point on the parabola. So what we're going to try and prove here basically is whenever light rays hit a satellite dish, they always go through the focus, yeah, under our formal definitions. So we're going to have to add a little bit to our diagram to do this. This is essentially what the challenge question is getting you to do, but it holds your hand a little bit. And actually, I think the first bit is probably the toughest bit. Okay, we're dealing with y squared equals 4ax, yeah? Now, I've actually set a equal to 1 when I've been drawing this on GeoGebra, but that was just to make the diagram nice and easy and make my point clear. Now, don't forget, on a parabola, you've also got the parametric definition you can use, and this is the same for all conic sections. The parametric definition comes in really handy when you want to deal with a general point on the conic, yeah, on the parabola or hyperbola or ellipse, whatever you're dealing with, yeah. If you want to deal with a general point on that particular conic, well, use the parametric form. It gives you basically any point on the curve, and it's just dead handy for this kind of setup. And the reason it's dead handy is for finding the general equation of the normal, and this is a normal to the curve. So let me just write that down, normal to the curve. That's just dead handy. That is the normal to the curve. So in order to actually answer this question, I think it does actually, yeah, it does mention that the line n is normal to the mirror at point P. Good, yeah, because the normal on any parabola will actually bisect that angle. Okay, so let's try and find the equation of this normal to the curve. It just seems like a sensible place to start. Obviously, my alpha 1 and alpha 2 are supposed to be equal here. I just couldn't find a way in GeoGebra of calling both angles alpha, so I've just called it alpha 1 and alpha 2. Okay, there's tons of ways you can find a normal to a curve. You've actually got choices when it comes to conics. Obviously, if we're finding tangents and normals, we normally need to differentiate. I'm going to differentiate. My choice, I could use parametric differentiation to differentiate this, but I think what I'm going to do is I'm going to differentiate this implicitly and then rearrange. So if I differentiate this implicitly, I get 2y dy by dx equals 4a. And hence dy by dx is 4a over 2y, which is 2a over y. Now, at the point I'm interested in, let's call this P. At P, which is at squared, well, let's just put at P actually. At P, dy by dx equals 2a over, right, I can sub in y now, 2at, which is 1 over t. Now remember, that's the gradient of the tangent. Therefore, the gradient of the normal is minus t. Now I can find the equation of the normal, and we're definitely going to be doing this in the next few exercises, so this is really good practice. We've got y minus y1, 2at, is m of x minus x1. Yeah, so I'm just using my y minus y1 is m times x minus x1. Dead handy, way better than y equals mx plus c for these equations. Trust me on that. Use this, don't use y equals mx plus c. Never use y equals mx plus c in conics unless the question requires it and asks for it in y equals mx plus c. Okay, we can now simplify that, and I think you'll see that you're going to get y plus xt equals 2at plus at cubed. Yes, I've just simplified it a bit and tidied up. Okay, that's my equation of the normal. Now, the reason I'm doing that is it wants me to find tan alpha first. And my thinking is, if I know that point, which looks like 6 on my diagram, but I'm showing it for the general point, if I know where the normal hits the x-axis, then I can start finding tan alpha from doing opposite divided by adjacent. This isn't necessarily the easiest way. This is just the way I saw when I was doing it a second ago. So, okay, let's set y equal to 0, and you're going to find that xt equals 2at plus at cubed. And so x is 2a plus at squared if we divide by t. Okay, great. I've found this coordinate now. Ignore basically my numbers on the axes because I'm proving this for the general point, whereas that's just showing you it for a specific value of t. Okay, so we've got 2a plus at squared, and 0 for our y component. Okay, bear in mind as well that if p is that coordinate, then this must be the line y equals 2at, yeah? And as we're going from 0 up to 2at, this must have a height of 2at, yeah? This is a slightly trickier bit, going from there to there. We're going to have to subtract the x coordinates now. And if you do at squared plus 2a minus at squared, you're simply going to get a length of 2a. Hence, and I would like to sort of justify actually in my working a little bit more. I've just justified it on the diagram. I don't like it when students do that, but I'm doing it like that now. But hence anyway, hence tan alpha, or tan alpha 2 if you like, is 2at over 2a, which is t. So we've proved tan alpha is t. That's the most difficult part of this question. I honestly believe that. That is the toughest bit. Okay, in part B, it wanted us to find an expression for tan 2 alpha. I'm not sure why they've asked you to do this, and it's obviously because, I'm certain though, it's because I'm doing it in a way which is different to what they were expecting you to do. That's often the case, but they've asked me to find tan alpha. That's just double angle formulae for tan, tan 2 alpha, double angle formulae for tan. It's 2 tan alpha over 1 minus tan squared alpha. And as tan alpha is t, we get the double angle formula for t. You're going to see this formula come up in t formulae. There's a whole chapter on this one formula, tan 2 alpha. Well, if t equals tan alpha, then tan 2 alpha is 2t over 1 minus t squared. We use that formula all the time later on. We really do. So that's very familiar to me to see that. Okay, what else did it ask you to do in part B? It wants you to find the gradient of the reflected ray. That's easy, yeah, because we already know that this is the focus, yeah? And the focus always has coordinates A, 0. So now we can find the gradient of the reflected ray just by looking at rise over run again. So gradient of reflected ray, that's going to be equal to, right, let's have a little look. It's risen by 2at. It's going to cross by at squared minus a. So we've got 2at over at squared minus a. You can obviously factorize the bottom or just divide everything by a. You get 2t over t squared minus 1. All right, looks like just a simple sign change from tan 2 alpha. Now I'm missing a real trick here, I'm certain of it, because I don't know what they're intending for me to do with the tan 2 alpha. If you do know, let me know. Send me an email and say, oh, you silly man, like you just needed to do that. But okay, so for part C, this is my way of doing it. But I'm not going to actually use that tan 2 alpha result. For part C, they just want us to show that that line definitely passes through A0. Well, I've got the gradient of the line and I've got a point on the line, P, so I'm just going to actually find the equation of the line and then show that that satisfies the equation of the line. So the equation of the line of the reflected ray well, that's just simply going to be y minus y1, and I'm going to use P for my point which lies on the reflected lines equation, equals the gradient, which we just worked out here, 2t over what t squared minus 1 of x minus x1. Yeah? Now, I'm not even going to bother tidying that up. And that's because I just simply need to show that A0 lies on this line. So I'm just going to now sub in A0 to prove it lies on the line. It lies on reflected ray. And what do we get? We get, right, we're plugging in y is 0 and x is A. Well, what have we got there? Obviously, we can take the A out of that and then divide both sides by A. Yeah, there's going to be an A popping out of that if you factorize it. So you're going to get 2t over t squared minus 1. But this is therefore going to be 1 minus t squared now. That cancels with the bottom and just changes the sign, and you get minus 2t equals minus 2t. And that is verified. A0 lies on line. Okay, I hope that made sense. That was just my way of looking at it. It's a lovely little challenge question, and the reason I like it is because it shows you why a satellite dish works. Okay, I will leave it at that, and yeah, best of luck with everything. Bye-bye.